Good morning, dear students. After the chemistry lesson, metals and non-metals, we are going to study about another physics lesson, important lesson, and the important phenomenon is studied in that lesson, that is magnetic effect of electric current. In this chapter, we are going to study about the effects of electric current through some activities, and we will get the knowledge of the electromagnetism. Children, in the last physics chapter, electricity, we learnt about the heating effects of electric current, right? Are there any other effects of electric current? We know that an electric carrying wire behaves as a magnet as long as current is passing through it only. We know that an electric current carrying wire behaves as a magnet as long as current is passing through it, children. In this chapter, we are going to study those effects of electric current and also studying about electromagnets, electric generators, electric motors, and much more about electromagnets we are going to study in this lesson. You might have seen the doorbell of your house. When guest comes and rings your doorbell, you can hear the sound of the doorbell, right? You can make out somebody has come outside, isn't it? You can make out that somebody has come to our house by hearing the ringing of the bell. That is very useful for us. On what basis, on what principle it works, children? It is working behind the principle of electromagnetic effect. That only we are going to study, magnetic effect of electric current. In 1820, the scientist Hans Christian Ørsted observed that current through a wire caused a deflection in the nearby magnetic needle. Ørsted placed a magnetic compass near a wire attached to a battery. You can see there, battery is attached to the wire. As electric current flows through the wire, compass needle deflected. You can see the deflection there, children, as long as current is passing through it. Ørsted has shown electric current generates magnetic field. This is known as electromagnetic effect, and the scientist Ørsted proved this theory. Let us understand the electromagnetic property by a simple circuit. The copper wire is wound on an iron nail. You can see there, we can see the paper clips are not attracted. Now there are paper clips. Simply the nail on which the copper is wound, it is not attracted. It will not attract paper clips. But when the ends of this paper clips are connected to a battery and this setup is brought near the paper clips, it will attract the paper clips. It is attracted. Isn't it amazing, children? You can see there what an amazing thing happened now. A nail is taken, copper wire is wound against it, and the ends of the copper wire is connected to a battery, and then paper clips, not only paper clips, any pins made of iron or steel, ferromagnetic substances are attracted towards it. What is an amazing thing has happened here? Why this happened? Here, whenever, as long as current is passing through the nail, it acts as a magnet, and it attracts the iron things or iron or alloys of iron, that is ferromagnetic substances. It will attract the magnet towards it. So by this, what we can understand, the current carrying wire can act as a magnet as long as current is passing through it. This is nothing but magnetic effect of electric current. This is the principle of that. Children, while explaining, I mentioned the compass needle or the magnetic compass. This you can see here is the magnetic compass. You can observe here it is a magnetic compass. Always see children, during olden days, people who are navigators are used to use this to know the seashores. To reach the land, they used to use this to know about that. This is magnetic compass or compass needle. Here you can observe red colored and white colored needles are there and the directions are written there, isn't it? This is a magnetic compass. You can observe children, it is nothing but a magnet. Do you know about the bar magnet? Yes, in your lower classes you studied about bar magnets, isn't it? It is also a small bar magnet. It always rests in the direction of north-south direction, children. Always it rests. Whatever turn you make, it will, in the end, it will go to its. If you move anywhere, it will rest in the north-south direction always. It comes to rest in the north-south direction, children. Anyway, if you move this, turn this, and you can observe that it in the end, it will stay stationarily in one direction, that is north-south direction, children. This is a magnetic compass. And here, when a magnet is brought near it, you can see the deflections there. When a magnet is brought near it, you can observe the deflections there, children. Are you watching the deflections there? Yes. There is deflection in its, the pointer is deflecting. The pointer of the compass, magnetic compass, is deflecting when the magnet is brought near it. But from the distance, very much distance, it won't deflect, children. Till where the effect of this magnet lies, till there only it will deflect. The compass needle, the needle of the pointer of the compass will deflect till the magnetic effect lies. Here you can observe, children, I have taken far from this. When it is brought near it, it has come to stationary now. When it is brought near it, you can observe the deflection here. I brought near it, so we can observe the deflections in the compass needle. This is very useful compass needle. If you move this anywhere, it will come to a stay or comes to rest in the north-south direction always. So, this is very useful in our magnetic effects. The experiments, it is needed, children. This is a magnetic compass or compass needle. Children, in the previous video, I showed you that a compass needle gets deflected when brought near a magnet or a bar magnet. A compass needle is in fact a small bar magnet itself. I told you about that, isn't it? It points always towards north-south direction. And here you can observe a bar magnet, children. Here see, there is a bar magnet. What is this? You studied about this in your lower classes, right? It is a bar magnet. There are two poles for the bar magnet, south pole and north pole. You can observe here, children, there are two poles. The end pointing towards north is called north seeking or north pole, and the other end that points towards south is called south seeking or south pole. Let us conduct some activities and let us know about the properties of magnets. In the previous classes, in your earlier the classes, you studied about the properties of a bar magnet. The like poles repel unlike poles attract. That is the main property of that we studied, isn't it? Now let us know more about the magnetic field and field lines. The region around a magnet where the force of attraction or repulsion can be detected is called a magnetic field, children. Wherever its effect lies, that is magnetic field. Magnetic field around a magnet can be detected by a magnetic compass also. Magnetic field lines now. The paths around a bar magnet along with the north pole of a magnetic compass tends to move is known as magnetic field lines. The magnetic field around, you can observe, children, here there is a magnetic field around a bar magnet. Now look at this. Here it is a bar magnet. What I told you, the paths around a bar magnet along with the north pole of a magnetic compass tends to move is known as magnetic field lines. You can observe some lines are there, some curves are there in this picture, right? The magnetic field around a bar magnet can be detected by sprinkling iron fillings around the bar magnet, children. Around the bar magnet, if you sprinkle the iron fillings, you can observe the pattern of magnetic field lines. Or you can follow other method also, that is by moving a magnetic compass around the bar magnet also we can detect the field lines. You can observe, children, here the curves are there. This actually what is that? Field lines around a bar magnet. This picture on the screen what you can see is showing the field lines around a bar magnet. We discussed about magnetic field, right? Magnetic field is a quantity that has both direction and magnitude. The direction of magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. Understood, no, children? So let us summarize the properties of magnetic field lines. The field lines, here you can observe, children, these arrows are there, no? These arrows or these curves are there, no? Those represent the field lines or magnetic field lines. What are the properties of these magnetic field lines? The field lines emerge from north pole and merge at south pole. That is the first property. You can observe there, the arrows are marked there. From where to where? Observe, children, there. Observe the arrow marks there. The field lines emerge from north pole. From north to south arrow marks are there. From north to south arrow marks are written there and it is pointed towards south. So, the field lines emerge from north pole and merge at south pole. That is the first property. Second property, inside the magnet, inside if you take middle one, you can observe, children, in the middle of the bar magnet, there are some curves there. Inside the bar magnet, the direction of field lines is from south to north. You can observe, children, from south to northwise. The arrows, observe the arrows there from south to north. Reverse of that before. Okay, that is the second property. And the third property, if you want to discuss, the relative strength of the magnetic field is shown by the degree of closeness of the field lines, children. Degree of closeness means what? How much crowded they are. The field lines, how much they are crowded. That shows the degree of, that is the strength of the magnetic field. The field is stronger, that is the force acting on the pole of another magnet placed is greater where the field lines are crowded. Wherever field lines are crowded, there the magnetic effect is stronger. Magnetic field is stronger. We can observe, children, there. That is another property of magnetic field lines. One more property is there. No two field lines are found to cross each other. You can observe, children, all are separately present in the pattern of field lines. No two lines are crossing over each other or intersecting each other. They are not intersecting each other. No two field lines are not crossing over each other or not intersecting each other. That is another property. If they did like that, suppose you think they are crossing over each other, two magnetic the field lines are intersecting each other, what would have happen? It would mean that at the point of intersection where they are meeting, at the point of intersection, the compass needle would point towards two directions, which is not possible. Simultaneously, magnetic compass cannot show two directions. Yes, no? So, this is not possible that two field lines can cross each other. It is not possible. They are not crossing over each other. They are separately present in the pattern of field lines around a bar magnet.